Hello, everyone. This is my presentation. It's .NET and WebAssembly back to the browser. My name is Larry Ewing. I'm an engineering manager at Microsoft. I lead the WebAssembly team in the .NET group. So basically, for this presentation, I'm going to go over a little bit of history of browser extensions, a little bit of details of what WebAssembly is and how it works, how we've combined it with .NET, and then who's using it, what it can do, and what we're planning to work on in the future. So let's get right in. So this is, in the beginning with the browsers, HTML was basically a static asset, so pages couldn't do a whole lot. From fairly early on, there were ways to extend the browsers. It started with plugins across different platforms. Microsoft had ActiveX, Netscape, and then Mozilla. Then, as they moved on, Firefox had NP-API. They're both basically based on native code connecting to the browser with COM. Some very memorable versions of those are Flash, and if you're a Microsoft and .NET fan, Silverlight, obviously. Also, Moonlight was an implementation of Silverlight for the Linux desktop. I worked on that team, so I've been doing strange things with .NET in the browser for a long time. There have been other attempts that weren't plugin based since then. Google, for a long time, advocated the NACL system, which is essentially native code compiled. It was essentially x86 instructions running in a sandbox. Then as they moved forward, they decided that it would be better to have platform-independent code, so they were using LLVM bitcode in what they called Pinnacle. And then, sort of as a response to that, to running native code, or at least native instructions or bitcode instructions in the browser, there was also a simultaneous effort to reduce down what parts of JavaScript you could basically define as very simple instructions, essentially a text-based assembly, and then highly optimize that set of instructions as long as you stayed within those instructions, and that was essentially ASM.js. So you produce JavaScript that's really only very, very tightly constrained, adds, multiplies, divides, things like that, and you can build an assembly, and you can build up basically an assembly language and run it. It worked quite well, but it also suffered from a very large representation. The text is quite large compared to some sort of compact format. So what comes next is WebAssembly. So WebAssembly is a low-level stack-based virtual machine. When it was first announced, they demonstrated support across several of the different browsers, Firefox, Google Chrome, Microsoft Edge. It's both a compact binary representation, and the specification also defines a text-based version, which is expression-based. The way that they decided to release it, they decided to define a minimum viable product, the MVP, which they released in March of 2017. And its goal was to have feature parity with ASM.js, at least on most things. So the idea was, okay, here's a compact representation. We're going to have feature parity with the ASM.js, and we'll move forward. The idea of the minimum viable product was they were going to focus on the basic parts of the virtual machine and then decide how they wanted to move forward with more instructions, and we'll talk about that later. They announced the plans in 2015, and so now this is what WebAssembly looks like. The binary format is a list of instructions, so you can sort of see what a transform between the C source gets converted into a list of instructions in the assembly, which is represented by the binary on the right. The text representation is a little bit simpler. It's expressions. It can either be very, very instruction-based, or it can sort of fold up expression-wise and be more compact itself. The usefulness of WAT is there's always a transform back from the assembly to the WAT file, so you can still effectively have a human-readable form of the binary in the browser. So basically, view source still works, which is useful in a lot of ways. You have a one-to-one translation. So here's an example of what a little bit of the mono runtime looks like compiled. This is the internals of the mono runtime compiled to WebAssembly, shown as a WAT file. The binary format is constructed of a list of sections. Basically, there's a type section, which defines all the function signatures in the entire body. There's the import section, which basically imports all the functions using the types that are available, and it basically defines the list of external callable methods that you have, so that's how you interact with the outside world. WebAssembly is a sandboxed environment. It can't reach out through anything but the use of the import declarations to interact with the system. That allows it to run in the browser very tightly constrained. Basically, it's only allowed to access those things, and the stack is opaque. And so then after the imports, there's the function declarations, which are the internal function declarations. They point back to the signatures in the signature table, which are in the type table, which is section, which helps a lot. And that defines the binary interface between your S. So you can basically, you think of it is essentially an assembly format, and with strong types on all the signatures. The next section is the indirect table, which basically allows you to do indirect function calls. Otherwise, everything would be static calls, and there'd be no way to basically modify your table. The memory section is your linear memory, which is essentially your heap. Everything that you read and write, everything that you modify in the program lives in the memory section. Everything else is not modifiable from the WebAssembly side. There are ways that you can modify it from the JavaScript side, potentially, but it's not defined on the WebAssembly side now. Then there's a global section, which defines your global variables. The export section, which the module both defines imports and exports. That way, it's like an assembly or a shared library, so you can export your callable interfaces to something else. Usually, or quite often, the JavaScript runtime that's also running side by side. But it can also be imported by another WebAssembly module running in the same context, so you can load up modules and connect them. Then the start function declaration is essentially the main. It's the entry point of your module, and then there's an element section and a code section. The code section is actually the function bodies, and it points back into the function table with a little indirection. And then there's data sections, and just like a normal DLL or other assembly that you would think of. There's opcodes. The opcodes that they define in the WebAssembly format by default are negative, because the idea is the ones that in the future, if opcodes move forward, or if there's a way to redefine opcodes, they'll start on the positive side. So basically, these are the types that are defined in the minimum viable product, the MVP. There you have integers of 32-bit and 64-bit size, and floats of 32-bit and 64-bit size. Then any func, which is basically a variable parameter function so that it can interact with JavaScript, since there's no version. And then func, which is the strongly typed within those types declaration. And then an empty block, basically, so that you can. Some sample instructions look like this. Memory size will modify your memory. The size of your memory table will grow. It's pretty common. These are very similar to other instruction sets. There's the binary representation, and then essentially the signature of the functions for each of those opcodes. So, if you're familiar with how .NET or how CIL works, .NET, these are very similar concepts. .NET also has a compact representation. It's a stack-based virtual machine. It has a much more expansive type system, but it could easily represent those types. So is there an easy way to transform it directly to WebAssembly? And the answer is not really. And why is there are a lot of rules of the way the types interact with each other. There's things like finalization and garbage collection that WebAssembly doesn't address at all. And so it's very difficult. You basically can't do a simple transform and enforce those rules. You need something to manage the rules that are defined by the specification. And so what do you have to do? Well, that's the idea here. So what we're going to do is combine .NET and WebAssembly. The basic idea is we'll compile the mono runtime, or any runtime. The C code, it's usually, the runtimes are often based in native code, C or C++ for both the CLR or the various .NET runtimes or mono. So we're going to compile the runtime to WASM itself. We're going to talk to the JavaScript bridge, or talk to the JavaScript thread to try and make sure that we can handle a few things that we can't do directly in WebAssembly. Disable the functions that we can't represent in the base class library, and we're basically done. Except that it's a lot harder than that. So what we had to do, most of the time, or modern .NET runtimes are JIT-based usually. There are versions of that. Mono actually started as an interpreter when we were bootstrapping the Mono compiler and the Mono runtime. It was an interpreter. We got away from the interpreter as quickly as we can because it's very difficult to have a high-performance interpreter. But we decided, well, since we don't have writable memory, we can't point, our code and data are separated strongly as part of the sandbox so that we can't escape the sandbox. We'll revive the interpreter. Now, in the mono runtime, the way that it handled certain things like exceptions or some of the more complicated bits of the runtime process was that it used inline assembly. We can't use inline assembly. Everything here has to be based as a WebAssembly instruction. Luckily, we had already sort of done a lot of this work in moving away from things like exception handling, which was written in inline assembly, and a few other things. We had already done a lot of the work so that we could support watchOS, because the way that you distribute watchOS is you take LLVM bitcode, and that's what you give to Apple, and then Apple makes sure that what gets delivered to the watch is something that can execute on the watch. That way, they can control the platform much more easily without you having to upload versions of different binaries. Basically, they take that LLVM bitcode and turn it into something that runs directly on the watch. And it also allows them to optimize, and we'll talk about that a little bit more. We also had to make fairly substantial changes to the BCL to support WebAssembly, and the normal runtime, especially the browser runtime, has limitations. We can't open a socket. There's no native file system. There's basically nothing. Some of the systems we use present a file system, and I'll talk about that a little bit more, but basically, there are strong limitations. There's also things like stack walking that essentially it's not supported because we have no control over the execution in the actual VM that we're running inside. And then we took advantage of excellent tooling, particularly LLVM, but tooling that really helped make this port from one to the other much simpler. Oops. So just in case, I've been talking about LLVM, just to let everyone know, it's a compiler tool set. It also defines an instruction set, and it's an implementation of that. It has excellent optimization. You can basically line up passes that will do expansion and reduction of the code flow to get you excellent code generation at the end. It can be incredibly slow, but that's the price you pay for some of the optimizations. And it provides C and C++, Objective-C and Fortran front ends, basically through Clang or other compilers that can target it. There's a lot of different languages that can now target LLVM, as you kind of saw as I talked about it. The other tool chain, which is more specific to what we've been using, is Inscripton. Inscripton basically is a front end for Clang and LLVM. Originally, it produced ASM.js. As of relatively recently, it moved to producing WASM directly. It moved to the fastcomp backend. The major benefit that it gives us is abstract, basically a standard library of function calls that look a lot like a standard C library or POSIX-like. So it gives us implementations of a bunch of the things that made bootstrapping the runtime much easier. So it does work. So what we have is we're allowed to run .NET code in the browser. It works across all the major browsers. You can actually run it on V8, or you can run it on headless on a normal JavaScript interpreter. And right now, the platform that we target is NetStandard 2.1. So you can essentially build a NetStandard 2.1 library and run it in the browser. So who's doing that, and what are they doing with it? Well, I work for Microsoft. The major component, the major driver of some of this work now is Blaser, which is part of the ASP.NET Core team. It provides a data model and a UI where you basically update your data model, pass it to the UI, and that interacts with the DOM in the browser. They've implemented two modes. One where the data model is like your model is computed on the server side, and the other mode is client side, where it's happening in the browser. And basically, you can flip a switch, and it'll either be running, your logic will either happen on the server and then send the resulting data to you, or it'll be computed in the client, and the data will be passed just over the bridge between JavaScript. I won't go too deep into their work, mostly because there are excellent presentations that the Blaser team has given that go deeper and better into the work they've done. There's also Uno platform. It's a cross-platform UI framework, similar. They're worth checking out as well. They have an excellent demo I could probably do here. Let's see. So this is a really fun demo. This is the original C++ source to the Windows calculator, compiled to a WebAssembly module, and then given a Uno UI front end and p-invoking into the WebAssembly module to call into the calculator. So it is code from a long time ago that works quite well. And under the hood, it's actually running locally, even though it's code from something like 20 years ago. This is an example of the Blaser, their default templates. We'll take a little bit of a look at them later and how it sort of works underneath. And then there's also Ewing, which was created by Frank Kruger, who started a lot of this work on our side. He's always been a part of the .NET world. I think he worked on WPF a long time ago. He's also done interesting projects for Xamarin, which I was a part of. And he created essentially a small UI toolkit that wraps several different versions of things, one of them being you can have Xamarin Forms running in the browser. And I don't know how many of you are familiar, but it's a cross-platform toolkit, XAML-based, that runs on phones, desktop, and now in the browser. I can show that a little bit later as well. So we have everything working. The big problems that we have are essentially speed. One of the reasons that everybody uses a JIT is because interpreters are slow. Size. Everything that we have to transmit, all the code has to make it across the network. Networking, as I mentioned before, the only platform that we can call into is what exists in the import section, and so that's what's available from the browser. So we have to conform to the networking aspects of that. Threading, which we'll talk a little bit more about later, because most browsers basically don't present more than one thread. There's one thread for JavaScript. There are ways to have second execution modes, and those are web workers, and we'll talk a little bit how we can combine those concepts and come up with something that looks a lot like threads. And then, because we have one thread of execution, things like GC become quite complicated because there's no way to stop the world across things and then do your collection as you normally would, or the various other modes of collection. But GC becomes more complicated. And then also debugging this, if we're trying to make a product, debugging can be quite tricky since you're running in a sandbox environment in a browser somewhere else. So we'll talk a little bit about that as well. So to work on the speed, not only are we an interpreter, but we're an interpreter running inside a VM. So that virtual machine that is inside the browser is a JIT itself. I think most of them now are tiered JITs, which means that they will do a first pass to quickly start execution, and while execution is continuing, they will re-JIT parts of the methods or the methods that you haven't hit yet, so that to try and speed things up in slower passes. And so each tier gets a little bit faster, but you pay for it with a longer JIT time. So the first step is we can look into speeding up the interpreter. Our initial interpreter, even when we revived it, was not highly optimized. So, and then the next step is looking into other modes of execution. So, like I said, basically there are 3 modes of execution that the mono runtime supports: the interpreter, the JIT, which is just-in-time compilation, and AOT, which is basically compiling the CIL to machine code, or in this case, to WebAssembly before in a compilation step, and then transmitting that instead of the actual normal assemblies that you would think of in .NET. There are also combined runtime modes that Mono supports now, which are mixed mode and hybrid mode. It's mixed AOT and hybrid AOT. The idea is some of your methods can be interpreted and some of them can be AOT'd, and there's good reasons for that we'll cover a little bit, and the same with the JIT. Now, because we don't have, it's very difficult to modify our own code, we don't currently support any sort of JIT in WebAssembly. This sort of covers what the benefits and problems related to each of the modes are. So interpreter mode, interpreting is slow. You have to figure out each instruction. In most interpreters, including ours now, there is usually a transform phase where we take the instructions that we get, we try to optimize them slightly, but it's not the same as JITting. It's a small transform. On the good side, the assemblies are small. I mean, it's as small as you can get, at least as .NET goes. We can make them even smaller with the IL linker or the mono linker, and I'll kind of cover that a little bit more. They're slower at runtime, but it takes very little time to get started or to go. And then it also supports system reflection emit, because reflection, like emitting your own code, is complicated when you can't execute things that you've written. So then in AOT mode, it's precompiled. You have faster executables, but they can be enormous. AOTing system XML, I think it was either iOS or WebAssembly, 13 megabyte assembly after AOT pass, which, since in the WebAssembly case you're talking over the network, that's quite a bit of overhead to be able to parse XML. The linker still helps. We can link the assemblies before we AOT, but it's no panacea. And then there's mixed mode, which is the mode that currently we're kind of focusing on our new development, which we AOT parts and we interpret parts and we try to pick the right parts. It lets us trade execution speed for size. It works pretty well, and it supports dynamic code because we can interpret that. It also allows us, for reasons that I can kind of cover later, to avoid some constructs that are difficult to AOT, so we can swap out those methods. For WebAssembly, size is really, really, really important. One, because everything has to go over the network. CDNs can help because they can reduce the actual network time, but the time to first load is always going to be your worst case. So reducing how much you have to load is going to help a lot. Also, if you're using bandwidth people are paying for, loading a 13 megabyte AOT code is not going to really make anyone happy. On top of that, the WebAssembly VM has to actually do its own JITting on the code that you're supplying it. So the more code you supply, the more work it has to do, and it has to do its optimization passes. And so basically, you're giving the VM that you're running in more work to do. So one of the easiest ways to fix that is use a linker. So what the linker does is it goes through, follows execution. You start at your entry points, it follows execution. Every time it visits a function, it marks it in the table that it's maintaining. It walks through assemblies. It looks, once it's ended its execution, it looks at everything it's marked and keeps it and then throws away the rest. Now, that can be fairly complicated and it often preserves way too much because it doesn't know, if it can't statically determine whether or not a certain path is taken, it's going to preserve both paths. So if there's an if statement, it'll preserve both of the branches there. There are ways to work around that. So we've been looking at the sizes in the assemblies in the base class libraries and saying, okay, are there places here where we can assume or fully determine that only one branch will be taken? If so, we can link out the rest. We can also, since we're defining a new API surface, we can get rid of parts of the API essentially by saying that it's not currently supported on WebAssembly. That's the way that the net standard APIs are defined to work. When an implementation can't do it or won't, then they can essentially throw platform not supported and after it's been defined. The work is ongoing. It doesn't have to be perfect. We don't have to fix everything, but we're trying really hard to target the parts of the assemblies, the parts of the code that are quite large. This is also important work because it's true of the upcoming work for .NET and everybody. The assemblies have grown quite large. There's been a lot of work in the base class libraries in .NET Core and going forward to optimize them heavily. That work has also produced, in some cases, quite a bit larger assembly sizes. So this problem is going to be even more pertinent across more cases. It's also quite pertinent for the Xamarin workflows for like iOS and Android, because that means your package, your install size, and your startup size are going to get bigger as if everyone's paid attention to the plans going forward, where we're trying to converge all of the runtimes, all of the platforms on a single set of class libraries. So we've also started writing tooling to help us do size comparisons, where basically we look at the input size of methods, assemblies, classes. We look for what's big, and then try to figure out why it's being maintained. We maintain as part of CI builds in Mono. We run the linker against existing applications and look at their size, store that data, and then produce graphs. These graphs are actually taken from a Blaser app. It's running in WebAssembly that talks to the GitHub API, pulls the data that's been stored there for each time the data changes, we commit a new, like an updated version of this data, and then that's what's building the graph. I guess I can show. There's also we have tree maps to break down the assembly sizes so that we can dig into what's gotten bigger and why. This is kind of ongoing work, but it will help. It's going to be used to help determine, and we'll probably release it sometime soon so that people can play with some of it themselves. So there are also, as I mentioned, different modes for AOT, but there's also different ways to specify how to, what assemblies you want to AOT. So in mixed mode, you can choose either by assembly or you can give it a profile. So the profiling lets you essentially pick a set of methods. So the way that the workflow works right now is you can generate a profile by executing the code. So Xamarin Android has just started using some of this in their builds where basically you start execution, you record all the methods that are hit as the program is running. Then you capture that profile, which is a record of everything that's been hit during execution. You can edit the profile, and then you pass that profile on to the AOT compiler in the compilation step, and you only execute the methods, or you only AOT the methods that are in that profile. aprofUtil is part of the tooling that helps do the editing of the profile. It's a mono profiler that you can load. You can load it in WebAssembly as well. And then you take the output of that profiler, and you can filter methods by class or by method itself. That way you can tune the profile. We're starting to make tooling to basically compare, as part of the linker step as well, compare the CIL size, the IL size of each of the methods versus the AOT'd size, and then we can take that and basically automatically trade off size for execution, because then we can test the execution speed of our profiled sample, and then hopefully we'll be able to generate a tuned pre-AOT'd step that runs in mixed mode that will give us a good performance bump. Some of the initial things, without tuning it very much, saw about a 30% performance improvement in the interpreter, with just basically only capturing a profile of startup. So nothing special, just basically getting from opening the page to the initial run, capturing that and doing it, and we saw about a 30% improvement in the execution speed. Now, all of that is a lot of tooling. So right now in the mono runtime, we have a tool for WebAssembly which basically allows you to handle all of these steps as one. It's a development tool that has these modes. Basically what it does is it runs the linker, the IL linker or mono linker against the assemblies to strip out as much as it can there. Then you can take whichever part of that and AOT it. Then we go so far as to, a lot of the interaction that happens in the runtime is internal calls between the runtime. We can statically determine which of those are hit in several cases and link those out as a normal, like a normal native code link step. So it is a lot of work, but it's giving us size benefits that are quite useful. And then also, there's an option to strip the methods that have been AOT'd. So there are reasons not to strip the method bodies, but after the linker step, there's a lot of metadata that's still contained in the assembly. So if that assembly is being used, you often need to preserve the metadata. So the bodies, a lot of the time, the IL will still be there. If you know that you're not going to end up back in that method, and particularly if you know the interpreter isn't going to call into there, you can strip the bodies, which can reduce the side more. This tool it's definitely a development tool. We're moving, hopefully within the time frame of .NET 5, or the next versions of things, where we will have this as a normal set of the builds that connect. These steps can actually apply to, well, many of the steps can apply to several different targets, including some of the other platforms like iOS and Android, or even the desktop. Not all of them. Sometimes the fact that we have such a constrained environment kind of helps with reducing the size. So that kind of covers what we're doing right now with speed and size. The next part is networking. So like I briefly mentioned before, networking is handled by the browser. The browser, at least in the case where you're executing inside the browser, networking is handled by the browser, and so you're constrained with what you can do. You can't directly open sockets. You basically have to follow a lot of the .NET base class libraries that have all sorts of nice features for HTTP requests are difficult to support exactly. What we can do is we've made an HTTP client handler implementation that basically does best effort to support the natural interface. If you use parts of it that aren't available, it'll either throw or ignore it. This is actually the same method that the .NET Core used when they changed basically the networking stack previously, when they went from native stack to managed stack, and it reordered some of the objects things, but rather than breaking code by if you used a particular method like proxy configuration, they basically ignored the step. In our case, the platform is not defined yet. as far as exactly what. So we have a little bit more flexibility to go ahead and throw to give you an indication that it won't work. But at the same time, you can install a NuGet package, link it with, build it as part of your app and use it. So we want to support as much as we can. We also support WebSockets using the browser WebSockets, which means that they're slightly more limited, but they do work in, it does represent, a connection to a WebSocket. So as I mentioned before, there is a model of threading for WebAssembly, and the basic idea is, since your heap is represented by a memory segment, and that memory segment, when it's created, is actually a JavaScript typed array, what you can do is, instead of using a typed array when you instantiate the WebAssembly module, you use a shared array buffer, or not a typed array, an array buffer, but use a shared array buffer, and then you can pass that same instance of the shared array buffer to a different worker, instantiate that as the WebAssembly module, and now you have a shared address space. You can do the same with your function tables, et cetera, and that way, now you have two threads of execution and what looks like a normal threading environment. This works in JavaScript as well. I mean, ordinarily communicating with a web worker is message passing, but you can do this same thing. You can share memory between them. Now, it was turned off due to Spectre. It was one of the attack vectors is that you could use timing attacks and get inside and figure out what was in that memory, and so they disabled it and figured out what's in the browser memory as well. They disabled it for a while. It's back on in Chrome. I'm not sure on the other browsers right now. It's experimentally supported in the WebAssembly runtime that we have. We build it as part of our packaging. We test it with things, but because it's not broadly supported, we haven't added as a normal mode of execution. If anyone wants to play with it, it would be helpful. As I mentioned, garbage collection can be kind of tricky. You can't preempt the JavaScript. There's no way to stop running. We have no control over the execution. So originally, basically, we would collect as soon as we transition back into JavaScript. That's when we know that the runtime isn't executing at that point. So we can start scanning the memory that we can see for garbage collection. That can be quite difficult because that can be quite problematic because if your code is in a type loop and isn't yielding back, it can easily eat memory. Now with work related to cooperative GC that's been ongoing also for console work, we now basically, when we need to allocate memory, we can also run the GC because basically we can stop ourselves. This works with threading as well. It's the same sort of thing, but in that case, you can't really, in the same way you have no way to signal a thread, you basically have to wait until you've synchronized, and then you can try to collect across the two threads. Right now, it's turned off by default because we don't want to impact our current users, particularly Blaser, but you can make a call to one of the exported methods, which basically enables the full GC that happens at allocation time and at other points as well. And then the next one is debugging. What are we going to do about debugging, and how are we going to handle it? The basic problem is that there's no definition of in the MVP of what debugging means. There's not even really a way to say that these are debug symbols. It's entirely up to you. When you're debugging JavaScript, browsers all implement some sort of JavaScript debugger, and then for languages because a lot of languages these days compile to JavaScript, there's also the idea of a map file, which translates locations in the JavaScript back into locations in the source, so for things like TypeScript or any of the other. So we can take advantage of that as well. But also, like I've mentioned before, we have a runtime inside a runtime. So the JavaScript side, unless everything is AOT, the JavaScript side has no idea exactly what's happening in the execution state of the runtime. So we have to come up with a way to deal with that. On the good side, DevTools, like Chrome has defined a way to interact with their debugger, and they allow interaction over a WebSocket from a remote port. So it's how you can do debug remote instances, and that can be quite helpful for us. So basically what we're doing now, the way that we're implementing debugging for the foreseeable future, we might try to expand it, but for the foreseeable future, we've created a proxy that sits on that WebSocket, talks to the browser on one end and whatever interface that you're using to debug on the other end, and rewrites the instructions. It talks to the runtime and inspects the state of the interpreter, and then rewrites that at something that looks like what the DevTools protocol supports and returns that to the interface. And so it's a complicated dance of running a debugger on one side and talking to the interface on the other side and rewriting it all in the middle. But it allows us to probe our own runtime state. We can look at what's happening in the interpreter. We can show variables. We can do all the sorts of things you'd expect. We can add breakpoints. We can remove them. And then another good point is that because WebAssembly is growing more and more and on different scenarios, but Chrome is actually, the DevTools protocol is being expanded to support more type information, wider types. Basically, until recently, the only type of number that you had in DevTools protocol was a JavaScript number, so you had a double. And that works for most things because you can just sort of say that it's double, but it doesn't work very well for things like 64-bit ints, which we would like to be able to debug. On the good side, they've added support for some of those things. They're growing. There's an ongoing effort to improve debugging. And even recently, I think at least Chrome has defined a way to do dwarf debug symbols inside the inside WebAssembly, and so now the Chrome debugger understands that. It helps. It helps us some, but not. It doesn't help with the problem of the runtime state. But here's sort of an example of what you get. Here's the Chrome DevTools debugger running. You can see a fair amount of state on the side. There's the call stack. Here's a similar thing running inside VS Code. Execution is stopped at a breakpoint, and you can see variable values, things like that. There's the call stack. Here's the source and the So I'll also show that. I think we can do a quick demo of that as well. Okay. Here is the Blaser app that I mentioned before. Bring up this code. Attach to Chrome. Click on the page that's the one I want to debug. It's connected now. I hit click. It's stopped in the increment method that's called by click. There's the button on click. Here we're inside increment. Now we can step. We can continue. Look over here. There's your call stack. Here's our local variables. If we step in, here's the current state in that method. Now the memory stream is an actual object. We can expand it. We can inspect the properties as we go along. We can also, move through the call stack. So it works reasonably well. We have more work to do, but it's ongoing, and we have plans to address a lot of the We test all of this code on every CI build. Where, we go through, we run the mono unit tests for the BCL. There's, it's on the order of, well, it's many, many thousands of tests, both from the mono in-unit tests and then the CoreFX X-unit tests. We have our own runner for X-unit, which basically is a simplified version of the X-unit text runner because X-unit itself exercises a substantial amount of the platform before you get to running a test. And some of those things are difficult to be sure that they're working. And we run it across all the major VMs like SpiderMonkey and V8. We're using some of those tests to sort of shape the API that we want to support going forward. And then the other big part of what we're working on coming up soon is following along with the WebAssembly working group and the work they're doing. There's lots of work happening. Almost all of them live under the GitHub WebAssembly org. Basically, the proposals live there. You can look at them live. You can see what's happening. Some of the interesting ones are WASI, which is, it's the WebAssembly, I'll go into it a little more. And then there's also, WebAssembly they don't have any intention to version the WebAssembly file. Basically, the plan is that you do feature detection, sort of like with JavaScript. There's a helpful little application that does that for you. And basically what it does, if you want to use the SIMD proposal, it tries to use that in code as it's been defined. If it fails, then it marks that flag. It's something like 200 or 500 byte bit of code that exercises all the current proposals and lets you know if they're supported. And then that way you can load a different runtime to fall back. The nice thing about having everything over the web is that you can just decide at that point which version of the runtime, and you can have optimized or featured out various different things at that point. So SIMD is actually really important for the future. CoreFX has used a lot of vector-based stuff to try and speed up common operations inside the base class libraries, and Mono has already been doing work on the runtime to handle those like vector ops and things like that that are supposed to be handled by SIMD in the runtime, and the proposal lives at WebAssembly SIMD, but basically our current thinking is that as soon as it has wide enough support, we can basically start supporting it. WASI is the WebAssembly system interface. So as I mentioned before, Inscription provides basically a standard library set. It looks a lot like a POSIX system, so it's easy to port, but it also is backed by implementations on the JavaScript side. So WASI is essentially defining imports for your system, for your base system, that don't depend on JavaScript and are also sort of tuned for the idea that you're running inside a sandbox. It's really, it's a lot of the effort behind it is coming from people that aren't running WebAssembly in a web browser. They're running it either in something like Node, where you can have sockets, you can expose more stuff if you want, or they're running it in some of the really very constrained runtimes that either precompile or are highly optimized only for WebAssembly, where there is no JavaScript. And so what it does is it provides a platform contract that you can implement, and then as long as you're only calling those calls, you can have access. There's things like Fastly, which is the edge cloud to CDN essentially, but you can export your logic that you want to run on the border of your cloud, on the edge of the CDN. You can write it in WebAssembly. They'll take it, they'll execute it on their thing because it's a sandbox server, and that way that you can distribute your logic in whatever form you wanted to write it in, whatever form you compiled. Right now, doing it with Mono, doing it with the .NET runtime is quite large, but it's an interesting thing, and we are still looking at slimming down the runtime as much as we can for cases like that. Also, Emscripten, which I mentioned before is what we use, has been doing work to base their abstractions on top of WASI as well. That way, as long as you're using the parts that that don't need JavaScript support, then you can be using WASI and potentially run in those constrained environments that don't have a JavaScript backing. And then, as I mentioned before, we don't use JIT on our platform, but there are possibilities to do it. There are some discussion. There are some working group proposals, but there's also ways with the existing code you could potentially write to a different module, load that module, and link. And I guess that's it. So thank you, everyone. If anyone has questions, they want to talk about any of this, I'll be around. I'm happy to go into it. So thank you very much.